We've seen some examples of organic syntheses now with alkenes, but now we're going to learn how to make a carbon-carbon bond using the so-called acetylide anion, and that's going to open up a whole bunch of doors for synthesizing different kind of compounds. All right, recall that sp hybridized carbons are weakly acidic. So you remember we can look at the hybridization. So let me draw, here's alkane, alkene, alkyne. All right, and each of these guys, if they lose a proton, we get these conjugate bases, all right, plus H plus, plus H plus, plus H plus. So this one is an sp3 hybridized anion. This one's sp2 hybridized. This one's sp hybridized. And what we remember about the these things is that the s character is important, right? If you're an electron and you're an s orbital, you can be very close to the nucleus. If you're in a p orbital, remember we have a node right through the nucleus, and you cannot be as close to the nucleus. So if you're an electron, you prefer an s orbital. In an sp3 hybridized orbital, it's 1 part S, 3 parts P, so it's 25% S. sp2 is about 33% S, and sp is 50% S. So the more S character means most stable. Right. And so the more stable the conjugate base is, the more acidic this guy is. So acetylide, acetylene, right? These hydrogens are, their pKa is 25. Alkenes, we say, is 44, and alkanes is 60. These are numbers you need to know. Water's 15.7. And remember, this is a log scale. So this guy is, what is that, 19 zeros? So this guy is 1 with 19 zero times more acidic than this guy. Right here we have the Kas. All right, so the point is that we can deprotonate alkynes to turn them into their conjugate bases, which are called acetylide anions. We'll talk more about them. So here, will this work? So remember, in order to predict whether or not an acid-base equilibrium favors the products or the reactants, you look at the pKa's of the acids on both sides. So the pKa of this guy, he'll act as the acid on this side. His pKa is 25. Water's pKa is 15.7. So who's more acidic? Water's more acidic, so this reaction is going to be completely reactant favored, which means hydroxide is not strong enough to deprotonate acetylene or an alkyne. Do this again. Here we have 25. This time we've used a stronger base. This guy is called amide. And this is ammonia, his conjugate acid. And what's the pKa of ammonia? About 35. So now who's more acidic? This guy is. So this equilibrium will lie on this side. So amide is a strong enough base to deprotonate alkynes to turn them into these anions. Right? Remember, anions are going to be nucleophilic and basic. Quick review, we saw this before, but we can predict whether these are going to be product favored or reactant favored by finding the acids on both sides. pK of 16 for an alcohol, primary alcohol, or methyl. 15.7, this one will be slightly reactant favored. This one now, who's more acidic? -2 is more acidic, so this one's still slightly reactant favored. 3.7 versus 15.7. This one is totally product favored. And this one was fun because they give you the pKb and the pKa. This guy's pKa then will be 14 minus 3.4. So 10.6. Is that right? Doesn't matter because this guy is way more acidic. All right, so this is a review of predicting which direction an acid-base equilibrium will lie. This is the important bit. So when you treat an alkyne, a terminal alkyne, right, we need this hydrogen with, this guy's called sodium amide. Remember, it's the sodium ion and amide ion, right? So we don't really care about sodium, but this guy is the one we're interested in. So this, again, is the amide ion. And his pKa, right, is, well, the pKa of his conjugate acid is 35. So that means amide is a very strong base. So here we have sodium amide. Quick aside, watch out for, so sodium metal and ammonia. Remember, this is how we reduce alkynes to transalkenes, metal and ammonia. Watch out for that because they look very similar, but they're different. So sodium amide is a very strong base. I deprotonate this guy and I make this thing, so nothing else changes. I have the anion here, and we would make ammonia, right? We don't really care about that, but it's true. Now this guy is a strong nucleophile. Alkyl halides are electrophiles, so this is my strong nucleophile. This guy's electrophile on carbon, right? He's electrophilic on the carbon attached to the halogen. And so what happens then is we have a substitution reaction where this guy forms a new bond to carbon, a CC bond. We have to break this one. And so what we did is nothing changed here, but I formed a new bond to CH2, CH3. And if we kind of keep track, this guy is this guy. So this one formed a new CC bond. And it's really important in this reaction that the alkyl halides that you use, you only have two choices. They can be primary or they can be methyl. That's it. What happens actually, well, let me say it right now. What happens with this, so if I try to treat this guy with a strong base, like an amide, this is a secondary alkyl halide or tertiary. What happens is we have a competing reaction. What is this one? Right, this is our elimination reaction. Right, whoops, dehydrohalogenation. So if you have secondary or tertiary, you do elimination. If you have primary or methyl, you do the substitution and form the new carbon-carbon bond. Right, so typically you can write this in two steps, like like this. So first step means turn it into the acetylide anion, like that. Right, then this guy's the next, he's the electrophile. This is methyl bromide, so this is allowed. This carbon's here, so what I make is this. Right, again, we're making a new carbon-carbon bond between this carbon when it's activated with amide and this carbon. Interestingly, what would happen if I treated this with another equivalent of NaNH2, and then, let's use CH3CH2, we'll use purple. What would this do? Because, wow, it's getting, come on now. Here we still have a primary or a terminal alkyne, right? So we can do this again. So a second equivalent, and we're going to form a new carbon-carbon bond between here and here. So now what we'll have is CH3, CH2, CH2, C triple bond C, CH3. Just mark it up like it was before. So this was the carbon-carbon bond we made in the first reaction. And this is the new carbon-carbon bond we made in the second reaction. So you can add two groups, two alkyl groups, methyl primary alkyl groups, to acetylene because he has two acidic hydrogens. All right, and what this then does is lets us do synthesis. So we know that we can turn alkynes into a bunch of different things, right? We've learned the reactions of those. We can reduce them to alkenes. We can turn them into aldehydes and ketones, halogenate them, hydrohalogenate them. But what we're going to see then is this guy now is a synthetic unit, right? These two carbons I can add to things and then do subsequent chemistry. So what I want to be able to do is look and find where are they in these products. So I could synthesize this guy from this, right? These two carbons could have been the original acetylide carbons, right? I would take my triple bond and I would reduce it. And these three carbons that I added, right, are just carbons that I added using my reaction above. So where could my acetylide, these two purple carbons, where could they be in this next alkyl chloride? They could be here, right? Or, I'm going to use a different color, they could be here, right? Because we know how to put hydrogens, right? There's a hydrogen there, or hydrogens and chlorines on those two guys. It would probably be better to use this one because if I had this, right, if I reduced it to the alkene, I have a Markovnikov side and an anti-Markovnikov side. If I use the purple, I have two equally substituted sides. So we have to think about the regiochemistry. This one, the two initial purple carbons could be here, or here, or here, right? They could be anywhere. But we would then reduce it with H2 palladium and carbon. This guy, the only choice is here. These must be my two purple carbons. This one, you can see that that is going to be the reactive bit. So what I'm going to do then is, let me just think about it this way. So starting again, I take my purple carbons, right, the acetylide, I add these 3 carbons. This guy, if I use the blue, I add 4 carbons using the acetylide anion synthesis above. Here, it depends on how I do it. I could do this, right, or other variations. Wow. This guy, this one's tough. This one probably had to just come with this whole stuff. This guy, I could add this and this, though, right? Add 3 carbons and 3 carbons to both sides. So this opens up the ability for us to make different molecules. So these are all the reactions we know, right? We can now use sodium amide to activate this carbon and form a new carbon-carbon bond. It must be primary or methyl, right? We can add HX, XS. They both go to the same carbon. We can make ketones. We can make aldehydes. We can add halogens, right? Excess halogens. We can reduce to the trans alkene. We can reduce with Linder's catalyst to the cis alkene. We can oxidize to carboxylic acids. And once we've reduced them to the alkene, we have all of these reactions available to us. So let's try some. So synthesize the following from acetylene. So the way I would like you to draw this would be start with acetylene and then draw arrows, write reaction conditions as go. So let's think about this. Let's draw one hexyne. So hexyne means 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6. Right? 1, 2, 3, 4, 5, 6. Yeah. 6 carbons. Got that. 1, 2, 3, 4, 5, 6. All right, so this is easy because what are we doing? We need to add 4 carbons to this. So step one, I treat it with sodium amide. That makes this carbon nucleophilic. Then I give it a substrate. I'm going to use this guy. 1, 2, 3, 4 carbons, and I'm done. Right, that one-step reaction will get me there, won't it? Yep. So here's my purple carbons, still here, right? And I added 4 more carbons to it. Again, the check. You have to remember that this guy must be primary or methyl, so that's okay. What about cis-2 hexene? So again, we're starting with this guy, and we want to make cis-2 hexene. So here's 1, 2, 3, 4, 5, 6. Is this cis-2 hexene? I think it is. All right, so based on this, where are my purple carbons? They must be in the middle here, right? So we can add carbons to both sides, and then we can reduce it. So I'm going to do this. Step 1, sodium amide, right, activates this carbon. Step 2, I'm going to give it ethyl bromide. That gives me this. Then step 2, do the same thing. Right, now what we have is, we got this guy. Last step, how do I get the cis alkene? H2 and Lindlar's catalyst. All right, so this is how we can synthesize that guy. What about 2-pentanone? Well, one means ketone. So we're starting with this guy again. 2-pentanone, so 5 carbons and a carbonyl, the ketone on carbon 2. All right, so we have a choice. We can make our purple carbons these guys, right, because a triple bond. Oh, I want blue. We could take that alkyne and treat it with oxymercuration conditions to get the ketone, or I could do the same thing here with the internal. Why is it better to use the terminal, though? Well, we'll see. Let's do it here. All right, so first step, I need to add how many carbons? 1, 2, 3. I need to add 3 carbons. So 1, sodium amide, 2, bromide. 1, 2, 3 carbons, right? It's primary, so that's allowed. Okay, I got 5 carbons in a row now. 1, That's good. And how do I make ketones from terminal alkynes? Mercuric sulfate, sulfuric acid, and water gives me the, right? Oh no. The Markovnikov enol, which tautomerizes to give me the ketone. What would happen if I did it this way and I had the, oh no, if I had this guy in the middle? 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. When I did oxymercuration, I would add the alcohol here and here. I get a mixture of ketones, wouldn't I? So again, you have to think about regiochemistry when you're doing these things. All right, here's another one. So we're going to synthesize these guys from this. So now we're problem solving, aren't we? One thing we can see, what are these? This looks like ozonolysis to me, doesn't it? So I think I'm going to have to make this guy, right? Where this is this, and this is this, right? And then if we did this guy, ozonolysis would get us there, right? O3, zinc, and acetic acid. All right, we cleave that, and we retain the vinylic hydrogen. Okay, cool. So the question is, can we turn this guy into that? So we need, what do we need? 1, 2, 3. How many, let's count our carbons here. That's the first question now, is do we have the right number of carbons? 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, 6. Ah, we do. All right. Oh, I see. We just need to put the double bond between 2 and 3, don't we? So can we do that? We need to move the double bond. Well, let me start here. I'm going to treat this guy with, oh, you know what? I'm going to use H plus and water. And I get the Markovnikov alcohol with rearrangement, which is this, isn't it? Then what happens if I do acid catalyzed dehydration? I look for my beta hydrogens. Oh, maybe this isn't the best way. Beta, beta, beta. Uh-oh. Let's see, I'll get this as a product, and I'll get this as a product. Oh, no, I won't. Oh, good news, it worked. What was I looking for? This one is tri-substituted. This one is di-substituted, so I'm not going to make it. Yeah. Oh, so we did it. Nice. Nice work by us. There you go. So we just turned this guy into these guys. Hashtag problem solving. 2 more. All right, we got to do this. So let's count carbons and see where we're at. So I got 6 plus 1 is 7 carbons. Here I've got 6, 7, 8, 9, 10 carbons. So I have to add 3 carbons. So let's have a think on this now. Can we, so I've got to add 3 carbons here, right? So can I turn this guy into the acetylene? If I was able to do this, then I could turn that into a nucleophile, right, and do the thing. But obviously, this is a fail, isn't it? All right, we can't do that. So what we're going to do is, let's do it the other way. So where can our triple bond, where must our triple bond be? Must be here. Those are the purple carbons, right? So this whole guy is this. So the purple will be the nucleophile, and the blue will be the electrophile. So what I'm going to do is I'm going to make this carbon electrophilic by brominating. If I used HBr, I'd get the Markovnikov. I don't want that. I need the anti-Markovnikov. So I'm going to use HBr and peroxides. Gives me this. Okay. Then I'm going to add CH3, C triple bond C minus. Okay, so I'm adding this already activated. So what we have to think is, how do we make that, right? If you're allowed to make it, then you can just kind of throw it in there. But if I treat this guy with sodium amide, right, I get that guy. So now these guys will react. 2, 3, and methyl. Oh boy, it got ugly. So the 1, 2, 3. Okay, yeah, I'm good. All right, what do we have to do now? Oh, easy. We have to, because there's my purple carbons, what do I have to do? I have to turn them into the cis alkene. So again, that is H2 and Lindlar's catalyst. All right, fun. Last one here. Let's count carbons. 5 plus 1 is 6. 1, 2, 3, 4, 5, 6. 6 carbon. Okay, we're not adding carbons, so we don't need the acetylide anion. How do we make carboxylic acids? I think we only have one way, right? If we take an alkene with a vinylic hydrogen and use acidic KMnO4, right? Alkynes would get us there too, but we don't need to add carbons, so we're not going to do that. All right, so if I had this, so then the question is, what alkyne or what alkene did we have? What would happen if this was ozonolysis or acidic KMnO4? Those guys plug into each other. So that's a ring with, how many things in the ring? 1, 2, 3, 4, 5. 5-membered ring. And this guy, and it looks like this, but let's see if I got that right. 1, 2, 3, 4, 5, 6. We got connecting 2 and 6. 2 and 6, yep. All right, so if I can get it to this, then ozonolysis will get me there, won't it? The question is, can I turn this guy into that? I didn't want you to do that. And I think I can, can't I? We only have 2 ways to make alkenes. Well, we got, 3 ways now? We can reduce alkynes to cis alkenes or trans alkenes. But this one, I'm just going to use good old acid catalyzed hydration. All right, I don't want to write it like that. I don't. H plus and heat, and the Zaitsev alkene is there. Oh, that's it. Oh, we're done. Nice. All right, so what you can see is with all the new reactions we have, we can play these fun games where we're starting to synthesize molecules using multi-step syntheses. And it really is just a puzzle, problem solving. Good time.